Okay, so this section is dihydroxylation. We're adding a hydroxy group to each of the carbons that are involved in a double bond. This particular section is on anti. We're going to do anti first, and then there'll be two mechanisms for syn dihydroxylation. So anti dihydroxylation uses a peroxy acid. This is an acid that has a carbonyl. It has two oxygens in a row, so it's kind of like a carboxylic acid except on steroids. The most common one you'll see is 3-chloroperoxybenzoic acid, and it will be abbreviated CMBPBA. So you'll see that will be what you'll see, and when you see that, you know you've got an anti-dihydroxylation reaction. So let's see how the reaction works. If we have a double bond here, we're going to have our peroxy acid above it. We'll have and there's the carbon, and there's the double bonded carbon, and there's our hydrogen. Okay, so we're going to have a bunch of different arrows. We're going to have about 5 arrows going on here. The pi electrons are going to be attracted to that oxygen. The electrons here are going to snatch that proton. These electrons are going to come down here, and then these electrons are going to go back to live on that oxygen. Okay, so a lot going on. That ends us up, it makes a ring. So let's draw the little ring here. We'll have a bond to the carbon, to the oxygen, another bond here. It'll be partially bonded to that hydrogen, partially bonded to an oxygen, and then this is the carbon we started with, and this is the other oxygen. We end up with this ring structure. The reason I've drawn it like this rather than the way it's drawn up here above is that I want you to see that all this is happening above the plane of the molecule. And what we make is going to be an epoxide. The epoxide sits above the plane of the molecule. That's important because when something is going to come in to attack, this is blocking it. Blocks the top, blocks top. So it's going to block the one side. So all the attacks are going to have to occur underneath. That's what's going to make it anti. We're going to end up with one on a wedge and one on a dash. So we've seen this before in a bromium ion and a mercurium ion. So here we've got our epoxide. And here we have an acid. This is an acid catalyzed reaction. The electrons here are going to be attracted to that proton, and then the electrons joining the proton to the oxygen will go back and live on oxygen. And that will give us an oxygen. It's going to be positive, and it's going to have a proton on it. Another water then is going to attach itself to one of these carbons. And then the bond between the green oxygen and the carbon is going to, those electrons are going to go up and live on the carbon. So that gives us, do the green, this one's going to be up. It's going to, oxygen still has the proton it stole. And at the other end we've got water. Now, it would be much easier to just add a hydroxy, because the next step is going to be to come in and remove one of these protons. So why didn't I just add a hydroxy? Well, I can't do that because This is acid catalyzed. There is no hydroxy. Okay, and that gives us this anti. There we go. One up, one down. So I'm going to skip and do B first because it's easier. So we'll have one on a wedge. One of the hydroxys will be on a wedge and the other will be on a dash. And we have to draw both configurations because these are not the same. Okay, and you almost have to get out the things to prove it to yourself. If you get out the models, if you look at them, this one's RR and this one is SS if you look at the configuration of these carbons. Okay, and if we do the next one, we're going to add a hydroxy here and I had a hydroxy here. One of them will be on a wedge and the other will be on a dash. And this one will now be on a dash and this one will be on a wedge. Okay, so let's go back and do the top one. The reason I left it is it's got these methyl groups and they will also be switching around. It makes it, I think, a little more complicated. So the original methyl group here will be on a wedge, and then we're going to add our hydroxy on a dash. So the hydroxy at this position will have to be on a wedge, and the methyl group that was already there is now on a dash. And then we just do the reverse. Oops. That's the methyl group, and that's the methyl group, and then we need to put our hydroxys on, one on a wedge and one on a dash. And that's done. That's this one. And I'll meet you with syn dihydroxylation next.